Hi everyone, welcome back again to this course on measurement and instrumentation, and today is the second lecture of our 12th week. Today we will continue our discussion on signal analyzers, and today motive is to cover a few more signal analyzers that we have seen in the last class as well. We have seen wave analyzers in detail. We will see some more analyzers like harmonic distortion analyzer, logic analyzer and some more. Okay. Before we actually go to understand the harmonic distortion analyzer, we have to understand what is distortion. Okay. So, if you talk about any ideal amplifier, okay, say if I have an ideal amplifier and if I have say sinusoidal input, and if the characteristic of this ideal amplifier is say linear, okay, this has a linear characteristic, the output is expected to be sinusoidal only, right. So, if I feed a sinusoidal signal to this ideal amplifier with the linear output, it can have certain gain or so, but it will be sinusoidal only. But if you see the practical amplifiers, we have a lot of distortion in the output. Okay. So, in real electronic circuits, the output waveform may not be exact replica of the input, even it has linear characteristic, because say this is made up of different transistors. Okay. So, they may have their own non-linear characteristics. So, overall they will have certain governance over the overall characteristic of this amplifier. Okay, or say if it is a simple op amp as well. Okay. So, they will have all this non-linear characteristic of this, the individual component will have certain governance overall output signature of this op amp or any other amplifier. Okay. So, therefore, you cannot expect it to be completely linear and it will be distorted. Okay. So, the difference between the input and output waveform in such a case is called distortion. Okay. So, if I have an ideal amplifier, input is say Vn Vm1 sin omega t, output will be say the input multiplied by certain gain, okay, and like this. Okay. However, in the practical amplifier, if you have input like this, you have the fundamental frequency f, and along with this you have the signal is kind of distorted and it has several other harmonics like second harmonic, third harmonic and so on. Okay. So, the distortion introduces additional frequency components that are integer multiple of fundamental frequency, which is known as harmonic distortion. Okay. So, the presence of these extra harmonic frequencies is actually the harmonic distortion that we are going to study and we are going to detect, because we are discussing about harmonic analyzer. Okay. So, the total output expected is actually I wanted only this Vm1 or say Vm1, I am telling that A V in, okay, if this was the input voltage. So, I was expecting only this, but what I am getting is this unwanted signals as V equal to Vm1 sin omega t plus Vm2 sin 2 omega t sin 3 omega t and so on. Okay. So, if the input frequency is f, the distorted output frequency may contain 2f, 3f, 4f and so on. Okay. So, there are different type of distortion that can occur, okay, from the electronic circuits, like I can have frequency distortion, phase distortion, as well as I can expect amplitude distortion. Similarly, we have modulation or intermodulation distortions, crossover distortions and so on. Okay. So, the frequency distortion occurs because the amplification factor of the amplifier is different for different frequencies. So, you do not expect the same kind of amplification for all the frequency component, okay, and therefore, there will be distortion. Okay. And this is even more common for the amplifiers which has even limited bandwidth. Okay. The phase distortion occurs on account of energy storage elements like inductance present in the system, okay, which causes the output signal to be displaced in phase with the input signal. Okay. If the signal of all frequencies are displaced by the same amount, the phase shift distortion may not be noticed. Okay. However, in actual practice, signal at different frequencies are shifted in phase by different angles, okay, and therefore, the phase shift distortion become noticeable and more prominent. Okay. Similarly, we have amplitude distortion. Okay. So, harmonic distortion occurs due to the fact that the amplifier generates harmonics of the fundamental of the input signal. This harmonics will always give rise to the amplitude distortion. For example, when an amplifier is overdriven and clips the input signal, we can expect the output to be clipped somewhere, and this is typical example of amplitude distortion. Okay. So amplitude distortion occurs when the input signal amplitude exceeds the amplifier's operation range. Okay. When this happens, the output waveform becomes clipped at positive, or it can be clipped in the negative peak as well. Okay. This clipping changes the original waveform shape and introduces additional harmonic frequencies. The other cause of amplitude distortion along with the overdriven input signal is incorrect biasing, or you can say wrong cue point of the amplifier. As clipping increases, the output waveform may approach even a square wave. You have input as a sine wave and you may end up getting a square wave, because of this amplitude distortion. Then we have crossover distortion, and crossover distortion is a type of nonlinear distortion that occurs in push-pull amplifiers. We have seen in the previous class also that many of the terminal stage of the systems that we are seeing have this push-pull amplifier as the last stage. Particularly the class B amplifiers dominate for this kind of application, and if you see, this is a typical example of crossover distortion. These areas are known as this crossover distortion. Okay. So this is, if you see, very near to the zero crossing point of the input signal. Okay. Then we have intermodulation distortion. It is produced when two different frequencies are combined or mixed together, or even you can expect it out of heterodyne circuit. Okay. We have seen what is heterodyne, super heterodyne in the last class as well. Okay. Now, when you are doing any kind of heterodyning, the output contains new frequencies equal to the sum and differences of the original frequency, something shown over here. Okay. When a high frequency signal, say F1, and a low frequency signal F2 are mixed in a linear circuit, the output contains only the original frequency F1 and F2. When the signals are mixed in a non-linear circuit such as a distorted amplifier, modulation occurs and the output contains all the components like F1, F2, F1 plus F2, F1 minus F2, say 2F1 minus F2, and so on. Okay. Now, additional harmonics and intermodulation components may also appear depending on what kind of distorted amplifier you have used. Okay. So, collectively all this harmonics can be called as total harmonic. Okay. So, if I say total harmonic distortion, it can be produced by any nonlinear systems that are used in this, any electronic circuit that are used in the data acquisition system. Okay. The harmonics consist of sine waves with frequencies which are multiple or multiplication of the fundamentals of the input signals. Okay. The total harmonic distortion, THD, is measured in terms of harmonic content of the wave and can be given as, the total harmonic distortion can be given as summation of harmonic square under root divided by the fundamental frequency, okay, or the fundamental signal. Okay. A measure of distortion represented by a particular harmonic is simply the ratio of amplitude of the harmonic to that of fundamental harmonic distortion, or we will name it as HD. Okay. So, when HD can be given as dn, dn is the distortion of the nth harmonic, let me call it d2, d3 and so on. I do not have any d1 because the first one I am calling it as a fundamental component or fundamental frequency. Okay. So, I have d2, d3 and so on, and this d2, d3, d4, d5, they are equal to E2 by E1. Okay. Or I can say that dn is equal to En divided by En minus 1. Okay. Or you can simply say it is not n minus 1, you can simply say E1. So, all will have E1 at the bottom. So, D2 or Dn is equal to En divided by E1. So, D2 is equal to E2 by E1, D3 is equal to E3 by E1. I have to keep this everywhere E1 because this is the amplitude of the fundamental signal. Okay. So, this D2 is equal to E2 by E1 and En represents the amplitude of the nth harmonic. Okay, and E1 represents the amplitude of the fundamental signal. Okay. So, the total harmonic distortion THD can be simply given as under root of D2 square plus D3 square plus D4 square and so on, where this D2, D3, D4 represents the second harmonic, third harmonic, fourth harmonic and so on. Okay. Or THD in terms of the amplitude of this E2, E3 and E4, I can be written as under root of E2 square plus E3 square plus E4 square and so on divided by E1, or I can say E1 square, okay, under root of E1 square. Now, percentage total harmonic distortion, which is the majorly used term, can be given as under root d2 square, d3 square plus d4 square and so on into 100, where d2, d3, d4 and all represents the second harmonic, third harmonic, fourth harmonic and so on. Okay, and percentage THD in terms of the amplitude values can be written as under root E2 square, E3 square plus E4 square and so on divided by E1 into 100. Okay. So, in a measurement system, noise is read in addition to the harmonics. So, you may not end up only measuring harmonics, but you may also end up measuring harmonic plus the noise component. And the measured total waveform has harmonics, noise as well as the fundamental, and will not only contain the fundamental frequency. Therefore, the measured value of the total harmonic distortion which you have measured is equal to summation of h square plus n square, where n is the noise under root divided by the complete signal, which is h square plus n square plus f square, where f is the fundamental and h is the harmonic and under root of it. Okay. So, this is the measured total harmonic distortion. Okay. Now, to measure this total harmonic distortion, I have a tool which is named as Harmonic Distortion Analyzer. So, ultimate aim of this lecture is to understand this Harmonic Distortion Analyzer. But before we actually go to the analyzer, we have to understand what we mean by the harmonics. Okay. So, let us understand this Harmonic Distortion Analyzer in little detail. Okay. The distortion analyzers measure the total harmonic distortion THD without indicating the amplitude and frequency of each component waves in the complex signal. Okay. We have already seen that the distortion occurs due to the non-linear characteristic of electronic component used in the circuit, say for example a transistor or say a diode and so on. Okay. A distortion analyzer measures the total harmonic power present in a test signal rather than measuring each harmonic separately. Okay. The simplest method is fundamental suppression method, where the fundamental frequency is removed using a filter allowing only harmonic components to pass. We will see the fundamental suppression method in detail. However, there are other type of harmonic distortion analyzers also, like we have a tuned harmonic distortion analyzer, we have heterodyne type of harmonic distortion analyzer. A more advanced harmonic distortion analyzer is also available in the form of digital harmonic distortion analyzer. However, the basic of a harmonic distortion analyzer could be understood from a fundamental suppression method, and we will see this in a little detail. Okay. However, let us try to understand all this in brief. Okay. Let us understand the tuned harmonic distortion analyzer. As the name suggests, they uses a tunable band pass filter to select one frequency at a time, and fundamental and each harmonic component, including the say other things that you have seen D2, D3, D4, okay, all are measured individually. Okay. Although they have very high accuracy, however, the process is time consuming because you have to tune this filter every time for all these signals to, because you want to measure all these harmonics individually. All right. So, the process becomes very, very slow. Okay. The other type of harmonic distortion analyzer is a heterodyne type harmonic distortion analyzer. This, as the name suggests, it uses a heterodyne principle where mixing with the local oscillator is involved. We have also seen heterodyne principle in our previous class. Okay. It converts signal to a fixed intermediate frequency, and all the harmonics are analyzed at this intermediate frequency level. Okay. We also have a digital harmonic distortion analyzer, which are, as I have mentioned, are the advanced harmonic distortion analyzer and use fast Fourier transform FFT for harmonic analysis. Okay. They display all harmonics in frequency spectra and can measure the total harmonic distortion as well as the individual harmonic component in the signal. Okay. Now, let us see the fundamental suppression method in little detail, because this is, as I have mentioned, if you understand this, other harmonic distortion analyzer can be understood very easily. Okay. This is the simplest method for measuring of this total harmonic distortion, where the fundamental frequency is removed using a notch filter and allowing only harmonic component to pass. Okay. So, now you have separated out the fundamental frequency and you are only allowing the harmonic component. So, total harmonic distortion can easily be calculated. These two, this figure A and figure B, okay, they are the simple block diagram of fundamental suppression harmonic distortion analyzer, and figure A, if you see, this has capability of manual reading of the total distortion, while the this has capability of measuring the ratio, okay, ratio of the two, fundamental and the harmonic. Okay. In both cases, let us assume that the signal source has some distortion, and this can be checked by reading its output distortion by connecting directly into the analyzer. Okay. In both the cases, the signal from the source is fed into the amplifier under test, and this generates harmonics as well as the original fundamental frequency. The fundamental frequency is removed by the notch filter as shown over here. Okay. So, you have a signal source, it is passed to an amplifier which is under test, and then it is the signal is passed to the notch filter. Okay. I have a switch SW which can either be connected to position A or position 1, or it can be connected to position 2. It cannot be connected to both together. Okay. So, let us consider that, I mean, if you see, this is basically done in manual mode. Okay. So, consider that this switch SW is first placed in position 1 and it is disconnected from position 2. So, it is now connected to position 2. So, means that what signal is this indicator showing is the, say, this signal goes from this signal source and it can come to this amplifier under test, and then it is passed through the to the inductor, because the switch 2 is now not connected. In this case, the total content of the fundamental and harmonic is measured, because you are completely passing the whatever the output of this amplifier is to the output. Okay. Then the switch is moved to position 2 to measure just the harmonic, because when you are placing this to switch 2, okay, or the position 2, this switch is connected to position 2. Here the signal that is received here is the signal which is passed from this amplifier, and this signal is passed from this notch filter. Okay. When it was connected to position 1, notch filter was disconnected. Here notch filter is now connected. Okay. In that case, you only have the fundamental frequency at the output. After disconnecting from switch 1, the switch is moved to position 2 to measure just the harmonic EH. Please note that now when it is connected to this point 2, okay, now the signal from this signal source is going to this amplifier under test, and it goes to a notch filter. Okay, and this notch filter, basically it's a band reject filter. So, a very narrow frequency range, which is our fundamental frequency, it is tuned to that, and this fundamental frequency is rejected. Okay, and only the harmonic signal is passed through it. Okay. Now, you are able to measure only EH. Okay. So, the value of total harmonic distortion can be found from this two position of moving the switch as EH by ET into 100. In first position, I have got ET, and in the second position I have got EH, and total harmonic distortion can be found as EH by ET into 100. Okay. Now, the second figure, figure B, is shown over here. Okay. This is an alternative arrangement, whatever we have seen just now. Okay. It is just alternative to that. Okay. Here the value of ET and EH are read together. Okay. So, if you see, I am getting the value from this notch filter through this RMS detector, as well as through this amplifier under test. I am also feeding it to a RMS detector and feeding it to a circuit which can give me the ratio. So, what I am doing is, I am not moving this switch from one position to other, I am calculating both the signals together or simultaneously. Okay. Now, their ratio is calculated and displayed as a total harmonic distortion on the indicator. For good accuracy, the notch filter must have excellent rejection and high pass characteristic. Okay. The filter also need to be tuned accurately to the fundamental of the signal source. This is difficult to achieve manually, and most distortion analyzer do this automatically. Okay. A common idea is to use various bridge configuration, and based on the bridge used, we have various methods for measurement in the fundamental suppression method. We usually use 3 different bridges, and somewhere you may also find that fundamental suppression method are of 3 types depending on what kind of bridge we use. I have a resonance bridge method, Wien's bridge method, and also I have a bridge T network method. Okay, let's see them one by one. The first is resonance bridge method. You can see that I have R1, R2 in 2 of the arms. I have a harmonic detector. I have shown it by showing a changeable or variable resistance, and in one of the arm I have capacitance and inductance in series, and then I have a test wave. Okay. In the resonance bridge method, the bridge circuit is balanced at the fundamental frequency by tuning the inductor and capacitor values. Okay. When the bridge is balanced, the fundamental frequency is suppressed, okay, and the bridge becomes unbalanced for any harmonic components. In case of Wien bridge method, the Wien bridge network works as a selective filter tuned to the fundamental frequency, as you can see over here. Okay. At balance, the fundamental component is cancelled in the bridge circuit, and only harmonic component reach at the output terminal, and they are measured. Condition for balance for this kind of Wien's bridge is C1 equal to C2 equal to say C, R1 equal to R2 equal to R say, and R3 should be 2 times of this R4 value. Okay. In this method, the bridge T network acts as a notch filter tuned to the fundamental frequency, and the inductor and capacitor are adjusted so that network resonates at the fundamental frequency. Okay. The application of total harmonic distortion analyzer is really wide. You can use it in the audio amplifier testing to ensure high fidelity output with minimal distortion. Okay. They are also useful in the telecommunication system evaluation to maintain signal integrity in transmitter as well as in the receiver. Okay. They are also useful in the signal generator calibration to verify the purity of the sinusoidal waveform generated by it. Okay. In power system, they are very useful to detect and quantify harmonics in electrical grids and loads. Okay. In electronic equipment quality control, they are also very useful to assess performance and compliance of circuits during the manufacturing process. Okay. So, this is little bit about the harmonic distortion analyzers. We also have a very useful analyzer that is known as spectrum analyzer, and you may have seen one of the spectrum analyzer present in your laboratory. Okay. Spectrum analysis, if you say, is defined as the study of energy distribution across the frequency spectrum of a given electrical signal. The study gives valuable information about bandwidth, effects of different type of modulation, and any noise signal or spurious signal generation. Okay. The knowledge of all these quantities and phenomena are useful in the design and testing of RF circuitries as well as any pulse circuitry. Okay. The spectrum analyzer separates a complex signal into its sinusoidal frequency components, allowing each component to be observed individually. Okay. The height of each spectral line represents the magnitude of the or amplitude of the signal component, while the position of it indicates its frequency component. Okay. They are used to analyze signal distortions, harmonics, noise, and spectral purity in electronic and communication system, and spectral analyzers are widely used to study the RF spectrum produced in any microwave instrument, but particularly if the signals are very close to each other. Okay. It is also used to measure attenuation, FM deviation, and pulse frequencies in electronics and communication systems. Okay. They can display a wide frequency range of the order of 2 to 3 gigahertz for general observation, or a narrow range of about 30 kilohertz for detailed analysis. Okay. Signals at microwave frequencies separated by only a few kilohertz can be clearly distinguished using a spectrum analyzer. Okay. Spectrum analyzer is classified into 2 major categories on account of instrumentation limitation and capabilities. They are audio frequency analysis, AF analysis, and RF analysis. RF spectrum analyzers usually work in the range of 10 megahertz to even 40 gigahertz. Okay. But before we actually see them, let's see a basic spectrum analyzer. A basic spectrum analyzer is shown over here. You have an input, it goes to a mixer. I have a intermediate frequency amplifier, then a detector and video amplifier, and it is fed to a CRO, and then a sawtooth generator, and which is fed into a voltage tune local oscillator. Okay. A basic spectrum analyzer displays a graph of signal amplitude versus frequency for selected portion of the spectrum. Okay. This spectrum analyzer mainly consists of a narrowband super heterodyne receiver and a CRO. A sawtooth generator provides a ramp voltage to the frequency control element of the voltage tuned local oscillator. Okay. The local oscillator then sweeps through its frequency range and mixes with the RF input signal, which is fed into the mixer. The resulting intermediate frequency signals is amplified, detected, and displayed on the CRO as amplitude versus frequency graph. Okay. It should be noted here that the same sawtooth voltage which is generated by the sawtooth generator is simultaneously applied to the horizontal plates of the CRO, which is shown over here. So, this is about the basic construction of a spectrum analyzer. Now, if I want to visualize a signal on a ordinary CRO, it will be represented as amplitude versus time, and particularly in the time domain, and the waveform will appear as a combined signal. So, individual frequency component cannot be clearly identified, as you can see over here. I have multiple frequency component signals like F1, 2F1, F1 plus 2F1 and so on. They seems to be merged and cannot be understood separately, while if you want to, or if you display them over a spectrum analyzer, you can clearly see their individual frequency component. Okay. So, the signal is displayed in the frequency domain or amplitude versus frequency at the screen of a spectrum analyzer, and each vertical line here represents a frequency component such as fundamental frequency F and its any other harmonic like 2F and so on. Okay. Now, we also have a logic analyzer present in this series of analyzers. Okay. And a logic analyzer is an electronic instrument used to capture and display multiple logic signals from a digital circuit or a digital system. It converts the captured signal into timing diagram, protocol decodes, or any state machine traces. Okay. Logic analyzers have advanced triggering capabilities to capture specific signal events, because all these are digital analyzer. They are used to analyze timing relationship between many signal to digital system. Okay. Logic analyzers are important tool for testing and troubleshooting any digital signals. Okay. They were developed with microprocessor based systems, required more input than oscilloscope could provide, and even you cannot think a digital oscilloscope as an alternative to this logic analyzers. Okay. They have multiple input channels, making them suitable for analyzing many digital signals at one time. They have higher acquisition rates and larger channel counts to keep up with the modern digital technology. Logic analyzers are important tool for debugging and developing digital systems. If you see a digital oscilloscope, they are used for general purpose signal viewing. It measures analog characteristic, for example, rise time, fall time, peak amplitude, and time between edges, and they usually have limited input channels, typically up to maximum 4. Therefore, when many digital signals must be analyzed together or simultaneously, a logic analyzer will be required. A logic analyzer is used to measure and analyze digital signals and have many input channels. As I have mentioned, it can go to as high as 136 compared to an oscilloscope. Okay. It does not measure analog details, instead it detects logic levels based on a threshold voltage. Say if the input voltage is above the threshold VTH, it is interpreted as logic 1, and if this is below this threshold, it is considered as a logic 0. Okay. Logic analyzers display signal as timing diagram, allowing analysis of setup time, hold time, pulse width, and any missing data. They also provide advanced triggering, high density probes, and analysis features useful for digital system debugging and verification. A logic analyzer connects to a digital circuit, captures its signal, and study them to understand how the system works. So, you have connect, setup, acquire, and analyze are 4 different steps in a logic analyzer. Okay. So, 4 steps are used to connect this logic analyzer. First step is connect. The logic analyzer is connected to a digital circuit which is under test using the probes. Second step is the setup, where we configure the threshold voltage, trigger conditions and signal channels. Third is acquire, where we actually capture or record the digital signal from the circuit. And final stage is analyze, where it examines the captured signal to study timing. We already have a threshold voltage in the setup stage, so it can now take decision of logic states, and then it can also tell about the system behavior. Now, there are points where you can use digital oscilloscope in place of logic analyzer, but then there are conditions where only logic analyzers can be used. For example, if I talk about a digital oscilloscope, they can be used to measure analog characteristic of signal, for example, amplitude, rise time, fall time and overshoots, and they are suitable for analyzing only when there are only few signals at a time with detailed waveform information. Okay. While the logic analyzers are useful when you want to debug and verify digital system operations, to trace and correlate several digital signals simultaneously, and to detect and analyze timing violations and burst transient in a digital circuit. Okay. They are also used to capture and analyze the timing relationship between digital signal and to trace embedded software execution and relate it to any hardware activities. Okay. So, these are some basics about the analyzers that are used in a data acquisition system. Okay. In the next class, we will try to understand different control systems that are used in a data acquisition system. Mostly they are based on certain kind of feedbacks. We will try to understand what kind of feedback are desired in a data acquisition system. Okay. And once we understand this data acquisition or support of this controllers or this feedback control systems in a data acquisition system, we'll see in the subsequent classes that how this data that has been already acquired are displayed and stored in a analog and digital systems. Thank you.